You are on a social media website. How can you edit the profile of another user just by having them click on a link you provide? Or even better, just by enticing them to open an email from you without clicking on anything. This attack is called cross-site request forgery, and unless the website actively protects against it, it can also be used to cause victims to purchase goods on e-commerce websites, initiate payments on banking websites, and in general perform state-changing actions on the server end. Welcome to Frank Stajano Explains. I am Professor of Security and Privacy at the University of Cambridge, and this is a lecture in my computer security course for second-year undergraduates. Today's topic is cross-site request forgery, also known as CSRF or CSRF. CSRF exploits cookies, so let's first recap the essentials of how cookies work. HTTP, the Hypertext Transfer Protocol, the fundamental protocol underlying the web, started out as completely stateless. The client just sent an HTTP GET request to the server, which sounds like send me the web page that is at this URL. And the server sends back a response with either the requested page or some kind of error message. There are ways to add parameters to a request, but distinct requests are independent of each other. Now, seeing the web as a platform on which to build distributed applications, developers soon recognized the need to create sessions. I select a fluffy toy on one web page, a lollipop on another web page, and then I visit the checkout page and I get a list containing both of these items in my shopping basket. So the technical mechanism introduced to add sessions on top of HTTP is the cookie. When the server responds to a request, alongside the response, the server may also send the client a cookie, which is simply a small piece of text with arbitrary content chosen by the server, and also an expiration date. The convention is that the client, the web browser, will attach the cookies it received to any subsequent request it makes to the same server, provided that the cookies have not expired yet. Of course, the client is free not to return the cookies or to return only some of the cookies, but functionality might then be correspondingly degraded because the server loses track of what the client had done in previous interactions. For example, the fact that I had selected the fluffy toy and the lollipop. If I don't send back the cookies, then the server will have no clue that I did that. One possible approach to using cookies to implement the previous example would then be for the website to send back a cookie containing the shopping basket. The content of the shopping basket is sent back by the server in the cookie. It lists all the items that I had selected so far. And then visits to subsequent product pages would accumulate further items into this cookie as appropriate, since I keep sending it back to the server every time I respond, or every time I get a new page. And when I instead visit the checkout page, then this would basically list all the items found in the cookie and offer me the option to pay for them. In this style of approach, the state of the transaction is kept in the cookie, so essentially client side. This relieves the server of the burden of keeping track of the state, but it has the disadvantage that the state can be manipulated by the client. If the cookie is in my browser on my machine and the server believes what's in the cookie that I sent it, then I could change the content of the cookie, and if I change what I selected, fluffy toy and lollipop and so on, it's not such a big deal. But if I am able to change the price of the items, for example, by manipulating this shopping list, then that would be a serious thing. So the alternative architecture is to make this cookie only basically a session ID, an unguessable session ID that refers to a session that is stored at the server. All the session state is kept at the server and is keyed by this session ID. Then in that situation, the client that returns the cookie to the server can pick up where it last left off in the previous interaction because all the state is remembered at the server, but the client is not at liberty to change the state between one interaction and the next. A session could be an authentication session, meaning, dear webmail site, I have logged in, so in all subsequent requests during this session, please show me my own emails until I log out of this session. And in this case, the first request to the site, which is the login, would involve some kind of authentication protocol. And the response to that would contain an authentication cookie coming from the server, possession of which would prove to the server that the client represents the previously authenticated user. Now, it's apparent that stealing authentication cookies would allow the thief to impersonate the victim. One countermeasure against cookie theft is the introduction of the secure attribute for cookies. If a cookie is marked as secure, then the client will only send it back in an HTTP request if the request is transmitted over a secure channel, such as HTTPS. Now, before delving into CSRF, another little aside about a different and much more common kind of web impersonation fraud than CSRF is, and that is phishing. Phishing is a very widespread but also very low-tech fraud in which the attacker simply reproduces the login page of a website and then sends the victim an email with a link to that website. Through a variety of social engineering tricks, such as appealing to greed, authority, time pressure, scarcity, and other principles that we will be looking at in detail in a future lecture on human factors, the email manages to persuade the victim to log into the fake website, where the crook then captures the username and password. No great sophistication is required on the part of the attacker for doing phishing, because the HTML of the login page of the target website can essentially just be copied verbatim, and there's no need to build any more than just a Hollywood facade because the website can simply pretend to crash after the credentials have been acquired. It doesn't have to actually work like the real website. The frontline technical countermeasure against phishing is HTTPS, which provides an encrypted channel where the endpoint is authenticated by a certificate. So this prevents the attacker from serving a web page that pretends to be the legitimate bank with a URL of www.bankname.com, because the certificate says, this URL is only associated with someone who knows this private key, and that is something that the attacker cannot fake. However, this technical countermeasure doesn't do the victims much good unless they make a point of checking that they are on the right website before entering their login credentials into it, which doesn't happen that often. Non-techies merely click on links without knowing where the links actually take them, and in any case, they can't easily tell the difference between the legitimate websites such as www.bankname.com or www.subdomain-of-bankname.com and the malicious websites, which to them look like the similar style of gobbledygook, such as www.bankname.domainoftheattacker.com or www.bankname.com with a misspelling, or www.domain-hack.com/www.bankname.com, or countless other variations on this theme, which just look legitimate if you're just parsing for is the bank name in there somewhere. So from the viewpoint of the crook, the fact that some of the prospects will be able to tell that the email is fraudulent is not a big deal. They can easily compensate by just sending out more emails to other people. You don't care much about having a low conversion rate if the per user cost of prospecting is negligible, as it is when you're sending out this spam. As for countermeasures, to the non-techies that ask me how they can protect themselves from phishing, I teach them how to bookmark their bank's login page, and then I teach them to type their credentials into the banking site only when they have entered it through that privileged route of clicking on the bookmark that they had previously set. Of course, this is a price that has to be paid for every website of value, so it's not an entirely effortless solution. Now, as for myself, I use a somewhat more geeky solution that I don't recommend to non-techies because I don't think it will work as well for them. And what I do is I simply refuse to give my regular email address to my bank. I either don't give them anything, or if they insist and they won't let me open the account or continue with the renewal of the account without an email, I give them another address that I don't use for correspondence with anyone else. And that way, if I ever get an email that pretends to be from the bank in my regular inbox, then I am 100% certain that it is a fraud, and I can very easily distinguish. A technical countermeasure that those in charge of the back end of the website can adopt is to enforce multi-factor authentication. And this largely defeats the fisherman because intercepting the other channels would be really difficult, at least if we are talking about dragnet phishing, where they're just trying to get millions and millions of victims, as opposed to the targeted spear phishing, where they can go to extra trouble just to get one individual. But of course, the introduction of multi-factor authentication comes with an extra usability cost for the users of the system, the regular users. Now we finally get to cross-site request forgery. This is an impersonation attack. The victim, Victoria, I'll call her, is logged into a website. I'm going to call it a wall bank. For example, it's a bank, an e-banking site, and the attacker, A for Albert, I'm going to call him, sends Wallbank a malicious request, which might be pay out some money, and Wallbank honors the request as if it had been initiated by Victoria. Because what Albert actually did was to trick Victoria into sending Wallbank the malicious request he had crafted. It's not the case that Albert crafted the malicious request and sent it to Wallbank pretending to be Victoria. He crafted the malicious request, sent it to Victoria, and persuaded Victoria to send it to Wallbank under her credentials. Albert can achieve this by enticing Victoria to click on some hyperlink, for example in an email or on some other website, that contains the malicious request to Wallbank. If Victoria was logged into her Wallbank account in some other browser tab in the background at the time she clicked on the link, then Victoria's browser, on visiting the malicious link, would attach Victoria's cookies to it, making it appear to Wallbank that the malicious request, which in fact comes from Victoria's client, is supported by Victoria's credentials. Notice that this is somewhat similar to phishing, but technically rather different from phishing. The similarity is that both attacks involve some element of social engineering, whereby Albert tricks Victoria into doing something without understanding what is actually going on. However, in phishing, the victim is tricked into performing the authentication protocol with the wrong website. She actually enters her credentials into the wrong website. Whereas in CSRF, the victim is only tricked into clicking on a URL without entering any of her credentials. And this is an activity that might seem safe. Okay, so after all, if you think what the victim thinks, say, well, I understand that entering my credentials might be risky because I might give them to the wrong website. But if even just clicking on links is unsafe, then what am I doing on the web in the first place? That's not an unreasonable thing to say. So in this sense, CSRF is more powerful than phishing in that it will catch out even relatively alert users who might be able to spot basic phishing and refuse to enter the credentials in the spoofed website. But it is an attack that is a bit harder to pull off than just plain phishing. The reason why the mere act of clicking on a link can be unsafe, even with an up-to-date browser, is because Victoria is already logged into Wallbank. Then this malicious link, which in this case isn't merely a request to view a page, but a request to perform an action at the back end, is executed by the website using the credentials that Victoria already presented to Wallbank when she first logged in. So how can a hyperlink also be an instruction or a command to the website? Let's figure this out. Everyone is familiar with web forms, at least as a user. Okay, the web page does not merely contain text and images, but also input fields that the user may fill in. Then there's a submit button. And when you click on the submit button, then this sends the content of those fields to the website. How does this happen? When the submit button is clicked, the browser sends the server one of two possible HTTP commands, depending on how the form was programmed. And they are get or post. In the case of get, which is the simpler of the two, the parameters are encoded as ampersand separated name equal value pairs in the URL that the client requests when the submit button is pressed. Whereas in the case of post, the parameters are encoded as part of the content of the HTTP request, the thing you don't see in the address bar. The format of post is a little more complicated to recreate manually, and it's more easily handled through some suitable library call. But it would be a mistake to think that you're only vulnerable to CSRF if you're using get, and if your website is using post, then the attacker would not be able to replicate that. That's not true, as we will see, as you will see as you do the seed lab for today. So here are examples of the two methods. Imagine that the website www.wallbank.com has a page with a form that allows you to pay money into another account. it displays two fields, the to for the destination account and the amount for the amount to be transferred. And let's pretend both of these are integers for simplicity. And there is a submit button. In the case of GET, the source of a bare bones web page might look like this, and it would render like this. The GET request to send £5 to account 12345678 sent by the browser to the website on submission of this form might look like this. And if instead we look at the case of POST, the source of the web page might look like this, which is the same as the previous one except for the forms method. And the HTML code would render as follows, which looks indistinguishable from the previous one. Now the POST request to send the same amount to the same payee is, however, a little different, and it would look like this. The parameters are no longer encoded in the URL, they're instead in the form data as part of the body of the HTTP request. And to see them, we need to inspect the request with the tools that are mentioned in your Seed Lab or Wireshark or any other method you like. And one of the things that are mentioned in the Seed Lab is the built-in tool in Firefox called the Web Developer /network. And if you use that, then it will show the form data for this request like that. Of course, what you're sending with GET or POST is ultimately the same content, of course, but it's sent to the server in a different way, a different format. With the POST request, if you give just the URL, then the parameters are missing. What does attacker Albert need to do in order to craft a URL that will cause Victoria, provided she's logged into Wallbank, to fill in the payment form with the parameters of Albert's choosing? For example, Albert's account number 6666666 and the amount of £5,000, without Victoria ever realizing that she is submitting a form to Wallbank. Well, in the case of GET, this is really easy. Albert just stuffs all these parameters into the URL, which gives something like this, and all that's left for him to do is to persuade Victoria to click on that URL while she is logged in. And he may do so with a totally unrelated email, click here for videos of cute cats or whatever, or with a post on social media, or even with a page on some other unrelated website that promises something enticing. Of course, he has no guarantee that Victoria will click, and he has no guarantee that she will be logged into Wallbank at the time that she clicks. And the two main levers that Albert has to increase his chances of success are to make the link more enticing to click on, is basically marketing, and to target a greater number of victims, greater reach. And even if his conversion rate is low, as we said, it costs him next to nothing to spam more people, and so all that matters to him is the product of these three quantities: the probability that the victim clicks, the probability that the victim has an open session with Wallbank at the time of clicking, and the number of victims that receive the link. And this, to a first approximation, gives the number of attacks that will result in a transfer of money to Albert. Now, of course, this is only a toy example to illustrate the technical issues around the CSRF. It's not a realistic depiction of actual scams, because for that, in order to make the attacks actually succeed and pocket some money, Albert would have to take into account the fact that the bank would trace him as the owner of this account 6666666, would have to take into account the fact that these payments are reversible, especially the ones between banks, and therefore he would need to start using unwary mules as intermediaries, who are the ones who are going to lose out on the money that gets transferred, and so on and so on. But we are not going there in this course here. Note also that to increase the first number, which was the likelihood that the victim Victoria would actually click on the link, he can also use a more devious technique of embedding the URL as the source of a 0x0 pixels image in an HTML email. Then, if the recipient's email client is configured to download images in incoming email automatically, then just receiving and opening the email will be sufficient to send the forged request, because the email client is thinking that it's just loading an image that was embedded in the email, whereas in fact it's sending this request for issuing a payment to Albert. And this happens without the victim having to do anything else, although it is still the case that the request will only work if the victim was logged into the website at the time of opening the email. Otherwise, the request will be sent without the necessary authentication cookies. However, it's not up to Albert to choose whether he's going to use the get or post in his URL. He must use whatever method is actually used at Wallbank. So if Wallbank is using a post instead of a get, what does Albert do? Well, he first must capture, observe, and take apart a genuine post request sent through Wallbank's form, and then he must recreate a form on his own attacker website that generates a post request in exactly the same format, except, of course, with his own chosen parameters. And you will be doing that in the seed lab. And then he must get Victoria to submit this form. While he might plausibly get away with persuading Victoria to click on a link, it would be a bit harder for him to persuade Victoria to submit a form for some random website. So what Albert the attacker can do instead is to craft a page on his own website that contains a hidden form and also some JavaScript callback that automatically, as soon as the page is loaded, submits the form. And this can be done in JavaScript. So if he sets things up that way, then the simple fact that Victoria visited the URL of his page, of the page on Albert's website, will be enough to send the post form to the Wallbank website. And then he will be in as good a situation as with get from the viewpoint of how hard his job is of persuading Victoria to issue the command to Wallbank. The following should be obvious by now, but let's say it explicitly anyway. The CSRF vulnerability is a form of impersonation, but it requires the victim, who's the prover in this protocol, to be already logged into the website, and the website is the verifier in the protocol. So this technically means that the website has deposited some login cookies into the victim's browser, and these cookies will be sent back to the server when the browser issues subsequent requests to the same site. The impersonator does not interact directly with the verifier. Instead, he causes the victim to interact with the verifier using her own genuine credentials, those login cookies, but requesting an action according to a template that was defined by the website, the verifier, with parameters that were chosen by the attacker. The attacker builds a request and through some social engineering tricks the victim into clicking on a link. And this action sends the malicious request, together with the cookies, to the website where the victim has an account, without the victim being aware that she did so. The attacker does not steal the cookies. He never even sees the cookies. He just gets the victim to present the cookies to the website herself, unsuspectingly validating the attacker's malicious request. What countermeasures do we have against this? Anyone who suggests that to counter CSRF we should tell users not to click on dubious links should fail the test as a security professional. This is unrealistic and completely counterproductive advice. The whole point of the web being such a powerful and revolutionary tool for disseminating ideas is this paradigm of clicking on links to sites you don't already know. It is up to us security engineers to make this activity safe, somehow protecting and sandboxing the activities of the browser so that clicking on a link cannot by itself have disastrous malicious side effects. The sensible way to counter this attack is to let the web server distinguish whether the request is cross-site or not. Ideally, the web server should only honor requests that originated from pages on its own site, and it should reject requests coming from elsewhere. But the web server can't tell the difference because of the statelessness of HTTP. On the client side, however, the browser can tell the difference, so it should be the job of the browser to let the server know. Of course, people can do what they like with their browser, including rewriting it so they won't follow the rules, but here, the browser in question is that of the victim, not of the attacker, so the victim has no incentive to make the browser misbehave and not follow the rules. And so, provided we can come up with some working scheme, the victim can protect herself by using a browser that complies with this scheme of telling the server whether the request it just sent was cross-site or was not cross-site. And it should not matter that it is possible for the malicious party to use a browser that does not comply with this scheme. In your textbook, section 10.5, there's a description of 3 such schemes for telling the web server whether the request was cross-site or not. First, the referrer header. Second, the same site cookie attribute. And third, the secret token. In the first of these schemes, the referrer header, The browser includes this header in the HTTP request, mentioning the URL of the page that the user was on when clicking that link. The trouble with this approach is that the referrer header is optional and it's often disabled out of privacy concerns at the browser end. So this would give rise to false positive, meaning requests that are classified by the web server as cross-site because they didn't come with a referrer header stating that they came from Wallbank, even though they weren't cross-site. It's just that the referrer header had been deleted. The second scheme, the same site cookie attribute, is a relatively new feature introduced by Google Chrome in 2016 and whose adoption and deployment, both by Google and by other browser vendors, has so far only been partial because of backward compatibility concerns. The third scheme, that of the secure token, is instead one that can be implemented at the web application level and therefore can be deployed immediately without waiting for all major browsers to adopt some common standard about the matter. The advantage is that a website that wants to protect itself against CSRF can adopt this scheme completely unilaterally without having to wait on any other party to do anything. The downside, of course, is that the scheme has to be re-implemented in every web application. The web application that's used as a target in the seed lab, called ELG, uses this third scheme of the secure token. And indeed, in the seed lab exercise, the countermeasure has been pre-disabled for you so that you can experiment with the CSRF attacks of tasks 2 and 3. And by the time you come to task 4, then you re-enable it. The idea of the secret token scheme is that the server embeds a secret in the web page with a form, and the browser repeats the secret when it sends the GET or the POST request. But the attacker is not able to incorporate the secret in his forged request because he hasn't seen the form. Why wouldn't the secret token be sent back to the server by the victim's browser together with the victim's login cookies? Well, because it is not held in a cookie sent by the server when the browser visited the page with the form. It is instead sent by the server through the page, and it's inserted back by the browser into a hidden field of the form before submission. So the attacker can't get the secret token to be sent along for free with the other cookies because it's not in a cookie. A new security token is generated by the web application on the server whenever it serves a page. It's created as the digest of the site secret value, the timestamp, the user session ID, and some randomly generated session string. The request from the browser will send the hidden field with the security token, but the fake web form that the attacker wishes to construct will not be able to include it. The timestamp is also sent along separately in plain text through another hidden field. This allows the server on verification to recompute the same secret and also to check that the timestamp is fresh to prevent replay attacks. The attacker cannot get the valid token by opening a new page on the server because the user session ID would be different. You'll be exploring all this in your seed lab. Cross-site request forgery is often confused with another similarly named attack, cross-site scripting. And I want all of you who are taking my course to have a clear idea of the difference between the two. And I want you to be able to explain it clearly to an intelligent teenager. If you're not sure about cross-site scripting, you might like to watch this other video. Thank you very much for watching, and see you in the next video.